All right, here we go again, part 2 of chapter 11. So we're talking about solubility and about other properties of solutions. So in terms of solubility, how the pressure affects solubility, what we're really going to talk about is the solubility of gases. So when we were talking about the effects of temperature, we were talking about if we have, a salt here inside of our solvent, and how as the water collides with, as the little water molecule collides with our salt, how pieces of these salt are going to break off into their component ions, and then those ions are going to float around inside the water, right? So when we're talking about an aqueous solution, we're talking about the amount of solubility of a solid. Most of the time. And then if we raise the temperature of that system, then water's going to be moving faster. It's going to hit that solid more frequently and with more force, and it can break apart that solid and stabilize more of these ions in solution, and then solubility is going to go up, right? And then if temperature decreases, the opposite generally tends to happen. So water molecules are moving more slowly, and when these ions collide with the salt, they're going to tend to stick and rebuild that crystal. Well, when we're talking about pressure effects, it's a lot easier if we are talking about gases. So the same thing that solids do inside an aqueous solution, gases can do as well. And a good example of this that we're all familiar with is the carbonation of beverages, right? Like carbon dioxide inside pop, carbon dioxide inside like sparkling water. All of these things are carbonated. And so when things are carbonated, what that means is that there is, inside the liquid, there are gas molecules of carbon dioxide dissolved inside that solvent. So the solute then is carbon dioxide. And then water, usually, if we're drinking it, right, is going to be the solvent. So we can talk about the solubility of gases inside these aqueous solutions as well. And then pressure is going to affect the solubility of these gases inside these aqueous solutions. So let's take a look at the effect of pressure here. Okay, so let's say we have a solution here of water. Now, if we have an open container of water, above it are going to be a bunch of different gases, right? If it's just open to the atmosphere, there's a lot of different gases floating around the atmosphere. We'll just name a couple. So as these gases are floating around our solution, they're moving quickly because they're gases, they're moving randomly because they're gases, and they are going to end up colliding with the surface of this water at some point in time. So as these gases collide with our solvent, sometimes there's interaction there. There's interaction between the solvent and the gas. And sometimes these gases end up entering and getting dissolved. Now, in the same way, if we have gases inside our solution, these gases are going to be moving around inside the solution. And as they do, they're going to hit container walls. And then at some point in time, they're going to hit the surface also. So if they hit the surface with enough force, they could actually break free out of the solution. And so here we have, if I switch colors, like in the case of this oxygen, this would be a rate of entrance. Our gas is going to enter our solution. If we're talking about this carbon dioxide here, this would be a rate of escape. Now, when we're talking about something like a carbonated beverage, where we have carbon dioxide inside the beverage, we have carbon dioxide outside the beverage, we can talk about the movement of this carbon dioxide in terms of rate of entrance and rate of escape. How fast is this gas entering our solution? How fast is this gas escaping from our solution? If the gas is entering the solution and escaping the solution at the same rate, then we are going to be in a dynamic equilibrium situation again. So remember, dynamic doesn't mean that whatever's trapped inside stays inside, whatever's trapped outside stays outside. Dynamic means we're continually having things enter, we're continually having things leave. That would be the dynamic piece. There's still change going on. But if we're at this point of equilibrium, that means the amount entering is equal to the amount exiting. And so we don't have a net change of dissolved gas inside of our solution. Now, here's where the pressure effects come into. Let's say we pressurize this. So we could pressurize this by, let's say we close the container and then we pump in more gas molecules. So we could just pump in a whole bunch of carbon dioxide molecules so that there's hardly any space above this solution anymore. And when we have so many molecules in there, the rate of molecules hitting the surface is going to go up. Lots of molecules there, lots of things hitting the surface. You can think about, I don't know, something that's fairly dynamic, like children, right? If you put one child in a bouncy house, occasionally they're going to hit the wall of the bouncy house, right? If you put 25 children inside a bouncy house, they're going to be continually hitting the walls of that bouncy house. And remember, force times area is going to equal pressure, right? So that's what we're talking about. We just force a whole bunch of carbon dioxide molecules into this one little space. All those carbon dioxide molecules are going to be moving around and hitting the surface of this water. We have increased the pressure of carbon dioxide above our solution. So when that rate of surface strike increases, right, more molecules hitting the surface, then more molecules are going to be forced into our solution down here. And that is our very definition of solubility, right? Solubility, the amount of carbon dioxide in our specific volume of solution. So increasing the pressure above it can force more molecules in, which changes how much will stay in the solution when that dynamic equilibrium of rate of entrance, rate of exit gets established. So the pressure effects of solubility, again, really have to do with the gas phase, gas being dissolved into our solution, rather than the solid phase, solid dissolving into our solution. Okay, so when we're talking about solubility, we can talk conceptually about solubility, but we can also back up our concepts with math. And that brings us to Henry's law. So Henry's law calculates the solubility of gas in solution. So that's the C. Remember, solubility is always a ratio. It's an amount of solute over the volume of solvent. So that could be measured in molarity. That could be measured in density. In the case of Henry's law, we're going to give chemists a break and we're going to measure solubility in terms of molarity. And then we see over here K. Now, K is a constant in this equation, but it's not a very constant. So what a constant is, we haven't dealt with too many of these yet. We'll continue to deal with constants throughout our curriculum, but all a constant is it makes an equation work. It's a number that's consistent and it makes an equation work. So in chemistry, we talked about like the relationship between wavelength and frequency, for example. Well, if you measure wavelength and frequency at specific temperature and pressure situations, contexts, then what you're going to see is wavelength and frequency always come out to have a set relationship. That relationship is very, very constant, and we can use one, therefore, to calculate the other one, as long as we know what that constant is. And in the case of wavelength and frequency, what is that constant? Hopefully you said it's the speed of light, right? The speed of light is the constant that makes that equation between wavelength and frequency work. Well, same thing here. We have K is going to be a proportionality constant. Now, unlike the speed of light equation, this K doesn't come with a concept. It's just a number. It's a number that makes it work. Now, the tricky thing about this constant is it's going to differ depending on your context. So it's different for each solute-solvent pair, and it also varies with temperature. And so if you want to know what the K is, you either need C and P to solve for it, or you need a reference. And so that's usually what we use. Somebody at some point in time sat down with a whole bunch of solutes and solvents, and they measured very carefully this relationship between C and P, and they determined very carefully what K is in all of these instances. And then they publish all of these numbers in a reference. And so we could go find the reference, which is probably a book, or more likely it's online somewhere. And we can look up, okay, for this solute and this solvent at this temperature, what is our K? Now, for our intents and purposes, since we are not necessarily studying in depth all of these things, we don't need to know the whole reference. And so usually they'll either give you the K for the equation that you're studying, or K is what you're going to be solving for. It's one or the other. So hopefully you won't have to look these up in a reference. But if you do, it's probably in the back of our book. Okay. Anyway, so we have C, which is solubility, right? We have K, which is the constant that makes the equation work. And then we have P. So what P is, it's a partial pressure of gas over a solution. So again, when we talk about gases, we're going to deal with partial pressure in depth. But what this is basically is a percent composition for a gas. So if you imagine you have a container, and in that container you have carbon dioxide molecules, and you have some oxygen molecules, and you have some nitrogen molecules. Okay, so if we want to know the partial pressure of carbon dioxide, we would take the part that is carbon dioxide, which in the drawing that I just made, it was 2 parts carbon dioxide, over all of the parts. So how many parts did I draw in there? 6? 2 over 6, right? So this would be the partial pressure of carbon dioxide in the example that I just gave you. It's a part over a whole. And we've seen this before. We saw this, I think, in our first unit. It's a percent composition. The only thing with percent compositions that you have to be kind of careful of is it's a percent composition by what? Is it a percent composition by mass? Is it a percent composition by volume? Is it a percent composition by moles? So that's the thing you need to know. And when we're talking about partial pressure is going to be a percent by mole. It's a counted number. It's a counted part over the counted whole. So it's in terms of moles. But usually on the AP test, when you're talking about Henry's law, you actually usually don't calculate anything in Henry's law. You use it to gauge like a change, or you talk about it relative to Henry's law. So for example, if partial pressure goes up, what's going to happen to solubility? It's going to go up, right? If partial pressure goes down, what's going to happen to solubility? It goes down, right? So that is describing this relationship between solubility and partial pressure relative to one another without ever actually calculating anything. Now, the second tip with Henry's law on the AP test is if you are ever asked about solubility and partial pressure, you should reference Henry's law. If you are ever asked about a relationship that is described in an equation, you should always reference that equation. That is your reason. We talk about how when you're answering free response questions, you should do claim, evidence, reasoning, right? Claim, tell them what your answer is. Evidence, tell them why. What do you have to stand on? So we'll talk about that in the next one, right? What's the data that was given to you? And then reasoning is like the explanation that connects your claim to your evidence. So if you can ever reference a equation for your reasoning, do it. That's a money answer. Okay, so for example, down here, it talks about champagne, soda, beer, and other carbonated beverages are bottled at slightly greater than 1 atmosphere. So 1 atmosphere is like if you are standing at the ocean on a lovely day, you would be experiencing 1 atmosphere of pressure. If you get to 2 atmospheres, if you are experiencing 2 atmospheres, you're going to know it. Your ears are going to pop. The jump between 1 and 2 is really big. So if you are talking about like the flux of weather, you're probably not going to talk about jumps in atmospheric pressure of 1 atmosphere. It's going to be like a tenth or a couple tenths of an atmosphere is your change in pressure. Atmospheric pressure when like storms roll in and out. Okay, so they're bottled at a pressure slightly greater than 1 atmosphere. So what happens to partial pressure of carbon dioxide when you take the bottle, you open it, and carbon dioxide bubbles out? So take a minute, pause the video, and think about it. Is partial pressure of carbon dioxide going to increase or decrease? Okay, and hopefully what you said was the partial pressure of carbon dioxide inside the beverage is going to decrease. As you lose carbon dioxide, we can think of our little molecule model over here. If we take one of these carbon dioxides and it bubbles out and it's no longer in our solution, now we have less carbon dioxide for the whole compared to the whole, and our partial pressure is going to decrease. So if our partial pressure decreases, what happens to our solubility? So this would be your claim, evidence, reasoning, right? So claim would be solubility decreases. Evidence would be your partial pressure has just decreased. And then the reasoning is because as Henry's law states, solubility of a gas in a solution phase is directly proportional to partial pressure. As partial pressure goes down, solubility is also going to go down. Claim, evidence, reasoning, that's how you should be answering any free response question that asks you to justify your answer. All right, so here's a problem that we can talk through when we're together in class next time. Okay, so we're going to get into a couple graphs. So before we kind of talk through this graph, I want you to look at it. Look at the x-axis, look at the y-axis, look at the title, and see if you can describe a general trend that you see going on here. Okay, so hopefully you picked up in this graph, this is solubility when we're talking about salts. So all of these things are solids that we're putting into solution, and it's showing how that amount that you can put in to the solution varies as temperature varies. So notice solubility over here on the y-axis. Notice that that is a ratio, right? Mass per volume, so grams per 100 gram of water. Notice it's all salts. All of them are talking about solids. Okay, and then we have temperature down here at the bottom. So we talked about how as temperature increases for a solid, solubility is also going to increase. So notice it's generally true. Generally, but not always true. It's very true for the red one, some form of astatine oxide. It's fairly true for the barium nitrate. Sodium chloride, it does increase as temperature increases, but not a whole lot, just slightly. The blue one, the dark blue one, sodium sulfate, it increases drastically to a certain point. And then after that point, it actually starts decreasing. And then for the light blue one at the bottom, the cesium compound, the cesium hydrate compound, it actually decreases. So we talk about how as temperature increases, the solubility of salts increases. That's generally true. And you can see here there are definitely exceptions. And there are also some things that it's not like drastically true for. It's just kind of slightly true for. Okay, let's do the same thing on the next graph. So look at X, look at Y, look at your temperature, and then look and see if you can give me a general trend. Okay, so hopefully you picked up out of here that this graph is describing gases. It's not describing solids like the last one. So it's describing the solubility of gases, and they have a pretty good sample here. So again, the Y is solubility, the X is temperature, just like on the last graph. And then notice also that as temperature increases, solubility of a gas does what? It decreases, right? It's actually the opposite. So as temperature increases, solubility of a salt tends to increase, but solubility of a gas tends to decrease. And I'm sure you have run into this before. Think about like if you open soda, right? You open soda, where are you going to put it? If you don't drink the whole thing and you want to save half of it, are you going to put it on the counter or are you going to put it in the fridge? You're going to put it in a fridge, right? Because you don't want that soda to go flat. And that's exactly what it's going to do if you leave it on the counter because it's at a warmer temperature. So a higher temperature has a higher rate of escape of the gas inside the temperature, inside the solution. And so that carbonation is going to leave. If you put it in the fridge, on the other hand, that carbonation is going to tend to stay longer so you can actually come back and enjoy that second half of your soda, right? Don't leave it on the counter. Who does that? Another place that you're going to see this relationship is in rivers and lakes. So, the big thing we're talking about in the environment is atmospheric warming. So as the atmosphere warms up, one of the concerns for rivers and lakes is that there's going to be decreased solubility of the gases that are inside those waters, right? Those waters need to dissolve oxygen because that's what a lot of the creatures inside those rivers and lakes depend on. They breathe too. And in order for them to keep breathing, there needs to be dissolved oxygen. The plants underneath the water, they need carbon dioxide to be dissolved in that water. And if carbon dioxide is not dissolved, then that oxygen isn't going to be able to take in that carbon dioxide and undergo photosynthesis, right? So as lakes and rivers increase in temperature, the solubility of the gases in those lakes and rivers is going to decrease. And those gases are going to actually exit out of the lakes and rivers. Same thing with something like when rivers are used for like cooling, like a nuclear power plant would be a good example of this. They pump water in, it cools the whole system off, and then they pump the water back out into the river. Well, the water that they pump back out into the river is now heated because it absorbed all this energy from the nuclear power plant so that the power plant could cool off. And it gets dumped back into the stream, and then there go the gases, because at higher temperatures, gases are less soluble. And so, the implications of this are all over the place. And you can see on the graph, this is fairly consistent. I mean, we don't have anything that's bucking the trend, except for helium. If you look at helium around 30 degrees Celsius, 30 to 40 is fairly consistent. But after 40, it does go slightly back up. But everything else, neon, argon, nitrogen, oxygen, krypton, xenon, everything else, the solubility decreases as temperature increases. So gases and solids are opposite. It's a good trends to remember. All right. So here we get into the math behind the solubility in these solutions. So let's take a minute, and I want you to go through these 6 things. Actually, not molality. Okay, so these 5 things, and see if you can write me a formula. So pause the video, see if you can write a formula for these 5 things real fast. Okay, here we go. Let's do this together. So mass percent we dealt with before. This is going to be a part. All of these actually are going to be a part over a whole. So for mass percent, that part over a whole is the mass of your solute over the volume. The mass of your solution as a whole, the whole solution, solute and solvent together. And then that's going to be times 100, and it's going to give you mass percent. Parts per million and parts per billion, these are counted parts. So it's going to be the number of your solute over the number of everything. So again, this is solute over solution, which is everything. Solution is solute and solvent together, added together. And so parts per million would be like the number of solute per million other parts. And by parts, they mean molecules usually, right? So like if you're testing like the mercury in a river, right? So how many parts of mercury, how many elements of mercury, atoms of mercury do you find per million molecules total? Parts per billion is usually going to be used like in atmospheric stuff. So if they measure like sulfur dioxide, for example, how many molecules of sulfur dioxide per billion molecules total found in the atmosphere. Okay, mole fraction. So a mole fraction is the moles of your solute over moles of your solution. Again, that's moles of solute, moles of solvent added together. And that is not multiplied by 100. That's mole fraction is always given as a decimal, and it's labeled chi. Chi. Okay, so this chi represents the mole fraction. So you can talk about like mole fraction of nitrogen in the atmosphere, and it would be the moles of nitrogen over total moles. So nitrogen plus oxygen plus carbon dioxide plus water plus everything else that's in your sample that you're measuring. Molarity, our favorite, after going through chapter 4, molarity is near and dear to all of our hearts. So this is going to be moles of solute over, nope, not moles, over liters of solution. Okay, so again, that's liters of solvent plus liters of solute added together would be liters of solution. And of course, that's going to be moles per liter or molar. Now, molality comes up once in one equation that we deal with, which is why we're not going to put a huge emphasis on learning molality. And actually, you don't even need to be able to calculate through the equation that involves molality. For the record, it's just another way to talk about concentration. So we've talked about density, we've talked about molarity, we've talked about all these other things, mass percent, parts per million, parts per billion, mole fraction. All of these describe concentration. Well, molality also describes concentration. Molality is going to be moles of your solute over kilograms of your solvent. Okay, so it's pretty similar to molarity. Moles of solute is on the numerator, in the numerator for both of them. The bottom for molarity is a total. The denominator for molarity is a total. Notice it's liters of solution. The denominator for molality is another part. It's not kilograms of solution, it's kilograms of your solvent. And so molality is like a part over a different part. So it's kind of weird. We don't use it a lot. We just see it in one equation, and you actually don't even have to calculate through that equation. So any book problem you come across that has to do with molality, you may skip it officially as of this slide. Okay, just one more time, I want to put at the top because it's pretty important. If you're talking about the solution, you are talking about solvent plus solute. So make sure when you're talking about the solution, you are allowed to separate that denominator into solvent versus solute. So for mass percentage, your denominator could be mass of solution, or it could be mass of solvent plus mass of solute. Same thing with mole fraction. Your denominator there could be moles of solution, or it could be moles of solvent, moles of solute. Same thing with molarity. Liters of solute plus liters of solvent, or liters of solution, whatever is more convenient for you. So when we start to kind of manipulate in and out of all of these things, you may want to separate that denominator out. So the next question is a pretty good example of, this puzzle, this thing that we're going to play with. Can you use these units and dimensional analysis and get from one thing to the next thing. Just a quick reminder, we'll go through this one together in class. You're going to have to play with it. You're going to have to be okay starting this problem and not having a clear path all the way through, and just kind of playing with these concepts and writing out what you know and looking at them from different angles. It's one big logic puzzle. So we have to find the joy in challenge when it comes to these, which you can do. I believe in you. You are worthy people. You are worth more than jewels. And you are worth the same whether you can do these questions yet or not. You may not be able to do them yet, but you will be able to do them, I promise you. So play with it, see how it goes. We'll play with it in class, and then we'll get together and talk about strategies. Okay, have a good day.